In the previous video, we talked about the semiconductor and the types of semiconductor. So basically, there are two types of extrinsic semiconductor, depending on the type of dopant. Right. So dopants are what? Dopants are nothing but the impurity atoms, the impurity atoms that you add to a pure semiconductor to increase its conductivity. So basically, if you dope with a trivalent impurity atom, what type of semiconductor are you getting? You're getting a p-type semiconductor. And if you dope with a pentavalent impurity atom, you're getting an n-type semiconductor. Got it? So p-type are what? They are the semiconductors in which holes are the majority. Holes are the majority charge carrier, whereas electrons are the minority charge carriers. That means in p-type semiconductor there are more number of holes than the electrons. On the n-type semiconductor, in the other hand, n is that mean or electrons, they are the majority charge carriers, whereas the holes are the minority charge carriers. So in n-type semiconductor, there are more number of electrons than the holes. Got it? Now, what will happen is, let's say we take a single semiconductor. Let's say I take a single semiconductor crystal. Okay, a single semiconductor crystal like this, and what I do, let's say this is a pure germanium crystal. Okay, this is a pure or an intrinsic germanium crystal. Alright, now what I do is I doped on one side. That means I add on one side the trivalent impurity atoms, and what am I getting? I'm getting the holes. Right, so holes are formed on this side of the crystal, and on the other side I dope with pentavalent impurity atoms, and I'm getting the electrons on the other side. Okay, so if I do this, you will see that there is a boundary that is separating the p side from the n side. This boundary here, that boundary. Okay, this boundary, it separates the what? The p side from the n side, and that boundary is nothing but a p-n junction. Is it clear? So how is a p-n junction formed? A p-n junction is formed by doping a single pure semiconductor crystal on n side with trivalent atoms and on the other side with pentavalent atoms. Got it? So what is a p-n junction? Basically, when a pure semiconductor crystal is doped on one side with trivalent impurity atoms and on the other side with pentavalent impurity atoms, a boundary separating the p side from the n side is formed. This boundary is called p-n junction, and the device as a whole is called a p-n junction diode, or simply p-n diode. Okay? Now what will happen as soon as the p-n junction is formed? So I want you to listen carefully, because this is a very important concept. All right, so let's say again we have this p-n junction. Okay, let me draw the boundary out here. Right, so let's say this is the p side and this is the n side, and we know the p side, there are majority number of holes, and on the n side we have the electrons. Okay. So right. So I want you to listen carefully and try to understand here. First of all, what are holes? Holes are nothing but, they're nothing but empty seats. Empty seats or empty spaces. Okay, they are empty seats or empty spaces that carry positive charge. Why? Because they basically are deficient of electrons. And we know that something deficient of electrons means it has positive charge. Got it? So here, these are just empty seats. You can think of this as a hall where on this side of the hall there are empty chairs. But here, this is packed with people. Okay, this is packed with electrons. Got it? So if you have like this, now mind you, I'm just drawing a boundary like this, but actually there is no such, this one is not blocked. All right, so the P side and from the N side, this is not blocked. Okay, there is no partition or something like this. It's just an imaginary boundary that I drew just to separate the N side from the P side from the N side. Now what will happen here on the N side, you can see that there are high number of electrons. That means the electron density is so large. Got it? But here the hole density is large. There are no electrons out here. Got it? So due to the high density of electrons on this side, there is a tendency for these electrons to move over to the other side. Yes or no? Because here they are all empty seats. So the electrons cannot stay compact like this in one place. So what happened as soon as the junction is formed, as soon as the PN junction is formed, the electrons from the N side will start to move over to the P side. Okay, so these electrons will move over like this. So therefore here, now you have the electrons coming here. You have the electrons coming there. So what will be formed out here? The holes will be formed out here. Do you see? So just on the other side, on each side of the boundary, you can see that there are electrons formed on the P side. There's a region where there are electrons on the P side, and a region where there are holes on the N side. Okay? So this diffusion of electrons from the N side to the P side, it continues until an equilibrium is attained. When will that equilibrium be attained? When these electrons now, which are present on the P side, will start to repel the electrons from coming from the N side to the P side. You see, when another extra electron goes this side, now it will face the repulsion of this electron. Got it? Similarly, when this hole is trying to go from P side to N side, it will now face the repulsion of this hole. Got the idea? So some kind of balance is attained out here. Some kind of an equilibrium is attained out here. Okay? So because of this, a new region is created in the boundary on either side of the boundary. Just in the boundary on either side. This new region has no mobile charge carriers, has no mobile charge carriers, and it is called the what? The depletion region. Is this clear? So what is a depletion region? The depletion region is nothing but the region where there are no mobile charge carriers on either side of the PN junction. Understood here? Another thing, what happened here? The holes which are on the N side, they will have a positive potential because holes are positive charge, right? And these electrons which are on the P side, it will have a negative potential. So because of this, there is some kind of a potential difference across the junction, and this potential difference is denoted by VB, which is called the barrier potential. Okay, or potential barrier. Okay. Another thing happens out here. Now, these holes and the electrons, there will be electric field. Let me draw with, let's say, a red color. there will be electric field which points from the positive charge to the negative charge. You see, this electric field is present only in this depletion region. And that electric field is known as the barrier field. Is this clear here? So many things happened, okay? Many things happened as soon as the junction is formed. So what do you do? First of all, you take a single semiconductor, a pure semiconductor crystal, and then you put trivalent atoms on one side, you get the p side. You put pentavalent atoms on the other side, you get the n side. So there's a boundary separating the p side from the n side. This boundary is called the p-n junction. Now, as soon as that p-n junction is formed, what happens here is that the electrons from the n side will diffuse into the p side. And you understand why that happened? Because there are so many electrons on the n side. So they are quite congested, okay? They're quite congested, quite compact out here. So what these electrons like to do is they like to go to a free region, right? They like to go somewhere else just to free themselves from being compact, from being congested. So these electrons, they drift from the n side to the p side. So when one electron drifts from the n side to the p side, one hole is formed on the n side. It's like a hole is going from the p side to the n side. Got the idea? So the diffusion of electrons from the n side to the p side continues until when? Until these electrons present in the p side will now start to repel the electrons from going to the p side. Similarly, the holes present on the n side will now start to repel these holes from going to the n side. So some kind of equilibrium is attained. Got it? So when that equilibrium is attained, a new region is formed where there are no mobile charge carriers in that region. And that region which is depleted of the charge carriers, that is known as depletion region. Okay? So when the depletion region is formed, you can see here that on the n side where there are holes, that region has a positive a positive potential because holes are positively charged, and these electrons has negative potential. So a potential difference is created across the boundary, and that potential difference is called the barrier potential. And what else? The holes and the electrons creates electric field which is directed from the n side to the p side. Okay, so this electric field is called what? Is called the barrier electric field. Understand? And this barrier electric field, let me take another page. Yeah, this barrier electric field EB, this is actually VB divided by D, where D here is the width of the depletion region. Okay, and the value of VB is different for different materials. At room temperature, VB is equal to 0.3 volt for germanium, and VB is 0.7 volt for silicon. Got it? So the barrier potential is larger for silicon than for germanium. Okay, so let's say an exercise. An exercise. All right. So here we have to find the barrier field. The barrier field in silicon. Find the barrier field. Find the barrier field for silicon semiconductor. Okay, the width of the depletion region is already given, and that is equal to 10 to the power minus 6 meters. So how do you find this? How do you do this? Very, very easy. VB is equal to, for silicon, let us use this formula. EB is equal to VB by D. And VB for silicon, we know that it is 0.7, whereas the value of D here is 10 power minus 6. So this comes out to be 7 into 10 to the power 5 volt per meter, which is very high. Okay, this value is quite high, right? Biasing of a PN junction. The process of connecting a PN junction to an external battery, this should be AN, to an external battery is known as biasing. All right. So there are two ways in which a PN junction can be biased. Forward biasing. Forward biasing. A PN junction is said to be forward biased if the positive terminal of the battery is connected to the P side and the negative terminal to the N side. As you can see here in this diagram, we have this PN junction. The P side, the P region, is connected with a wire to the positive terminal of this battery. And the N side is connected with the wire to the negative terminal of the battery. So P to positive terminal, N to negative terminal. Such a connection is known as forward biasing. And reverse biasing. A PN junction is said to be reverse biased if the positive terminal of the battery is connected to the N side and the negative terminal to the P side. Okay, this is just the opposite. P to the, I think I made a mistake out here. P should be to the negative terminal. Okay, so this one must be longer. Yes, this must be positive and this must be negative. Got it? So if you connect the P to the negative terminal and the N, a PN junction is said to be reverse biased if the positive terminal is connected to the N side. The positive is connected to the N side and the negative terminal is connected to the P side. Okay, so we have the two types of biasing, forward biasing and reverse biasing. Characteristics of a PN junction diode. The forward characteristics, what are these? These are graphical relations between the forward bias voltage applied to the PN junction and the forward current through the PN junction. Okay, so now what will happen if we forward bias a PN junction and we vary the biasing voltage? So let me draw the PN junction once again. So let's say we have this PN junction like this. This is the boundary. Then you have this is the P side and that's the N side. Then this wire, the P is connected to the positive terminal, whereas the N side is connected to the negative terminal. And V here is the biasing voltage. Okay, you remember that in the P side there are holes, right? There are holes like this. And we have the depletion layer. Okay, so that's the depletion layer. All right. Now what will happen? Just have a look here. As soon as I plug in the key, so let's say I have a key somewhere here. Okay, as soon as I plug in the key, what will happen? I am actually applying a negative potential on the N side and a positive potential on the P side. Got it? So what will happen? These holes which are positive charge, they will be repelled by the positive terminal. Similarly, the electrons which are negative charge, they will be repelled by the negative terminal. So the holes will start to move this way. Okay, they will start to move towards the depletion layer, towards the boundary, and the electrons will start to move also towards the boundary. Can you see? Why are they moving like this? Because of the repulsion that they face from the terminals. Got it? So basically, if this happens, then what do you think will happen to the width of the depletion layer? First of all, the width of the depletion layer was this much initially. So because these charge carriers, they are pushing onto the depletion layer, you can see here, right? So the width of the depletion layer now will decrease, okay? It will decrease, it will become smaller. Do you see? It becomes smaller like this. So now the width becomes this much. Some of the electrons from the N side, they cross over to the P side. And similarly, some of the holes from the P side will cross over to the N side. You see? So electrons will go like this. They will cross over. They will cross the boundary. This electron will cross the boundary and it will come here. It will come here. Whereas this hole, it will go there. Okay? So in this way, there is a crossing of charge across the boundary. The electrons will cross over to the P side. The holes will cross over to the N side. So due to the crossing of charges like this, there is flow of current in the PN junction diode, in the crystal. Alright. Now if you draw the variation of current with voltage, okay, we plot voltage in volt along the x-axis and the current in milliampere along the y-axis. So what happened here, as you increase this voltage, and there will be more and more electrons crossing. Okay, as you increase, that means the repulsion offered by the positive terminal onto the holes and by the negative terminal onto the electrons become more and more. It becomes stronger and stronger. So these electrons now they start to push more and more onto the depletion layer. So the width of the depletion layer keeps on decreasing. Now it becomes this much. It keeps on decreasing. So as the width decreases, what happened to these electrons? These electrons, they start moving. They start moving like this. More and more electrons will start moving from the N side to the P side, and more holes will start moving from the P side to the N side. So there will the number of electrons and holes crossing the boundary will increase. So in that way, the current will increase. It will increase like this. Okay? Until at a certain potential of, let's say, 0.7. This is if this is a silicon. For at 0.7 volt, what happened here is that the depletion layer, it ultimately collapses. Okay. What happened? The depletion layer ultimately collapsed. There is no more depletion layer out here. So when there is no more depletion layer here, now there is a free movement of charges from the N side to the P side and from the P side to the N side. Now this behaves as a conductor. So how does the current increase from there onward? From there onward, the current will increase linearly. Okay? Beyond 0.7 volt, the current will increase linearly. Here, the current is increasing how? Exponentially. Exponentially. Got it? So, but then beyond 0.7 volt, the current will now start to increase linearly. Is this clear? So this graph, which shows the variation of current with voltage, with the applied biasing voltage in the forward region, this is called the forward characteristics. Understood? A very important point to note out here is this part of the graph. This part of the graph. This voltage 0.7 volt, beyond which the graph becomes linear and below which the graph is exponential. This is called the knee voltage. Okay, so this is the forward characteristics of a PN junction. The reverse characteristics. These are graphical relations between the reverse bias voltage to the PN junction and the reverse current across the PN junction. Okay, now again, let me draw the PN junction once again. Let me change the color to white. Okay, so you have this PN junction and you have this boundary. Right, so this is the P side and that's the N side, and then this P is now connected to the negative terminal, whereas the N is connected to the positive terminal. Okay, V here is the biasing voltage. All right, so on the P side we have the many holes, and on the N side we have the many electrons. All right, so this is the depletion region, where here you have the electrons and here you have the holes. Okay, so now as soon as the key is plugged in, suppose this key is plugged in, then what will happen? It's like you are applying a negative potential on the P side and a positive potential on the N side, right? So this positive potential, it will attract the negatively charged electrons. Similarly, the negative potential will attract the positively charged holes. So these holes will go this way now. Yes or no? Are they moving towards the junction? No, they are not moving towards the junction. They are moving away from the junction. Can you see? They are moving away. So is there any crossing of charge across the junction? No, there is no crossing of charge across the junction, right? So what will happen to the width of the depletion layer? This is the original width. Because the charges are moving away, they are moving this side and the electrons are moving that side. The width of the depletion layer will increase, okay? It will become larger. Okay, it'll become larger like this. It'll increase now. Can you see? It has increased. And obviously there is no crossing of charges, right? But then what? Didn't we say that in a P side or in a P-type semiconductor, of course, the holes are majority charge carriers, but there are also electrons, which are the minority charge carriers. Yes or no? Similarly, on the N side, there are holes, which are the minority charge carriers. That is what we have discussed before. Yes or no? It's not that just because this is P side, only holes are there in the P side. No, the electrons are also there. But then the number of electrons in the P side is very few. They are minority compared to the number of holes. Similarly, the number of holes in the N side is very few compared to the number of electrons. Understand or not? Now, if you look at these minority charge carriers, this biasing is actually forward biased to them. Yes, it's actually forward biased. So it's actually you are applying a negative potential to this negative charge. So what will happen to this negative charge? It will move this way. Right? It will move that way. Similarly, this positive potential will repel this minority holes out here. So there will be motion of minority charge carriers across the junction, and because of this, a very tiny current flow in the PN junction. So how will the characteristic look like? So again, this biasing voltage is measured in volt, and the biasing current now is measured in microampere. So because of the motion of these minority charge carriers, there will be a very small tiny current present out here like this. Okay, very small. The current is practically zero, but this current is is very tiny, and it's due to what? It's due to the minority charge carriers. This is known as the reverse saturation current. Got it? What is the reverse saturation current? It is the current in the reverse characteristics, or during reverse bias, which is due to the minority charge carriers. Understand? Okay, now what will happen? If you increase this voltage more and more, then what will happen to the width of the depletion layer? Let me draw with green now. The width of the depletion layer will keep on increasing. Yes or no? It'll keep on increasing. So what happened here? This space becomes larger, right? So these electrons, when they move through this space, they get accelerated. They get accelerated. They are moving freely in this space. They get accelerated, right? So because they get accelerated, what will happen? If they, once they reach the other side, they go and bombard these atoms which are present on the n side. Suppose this is the atom, okay? Suppose this is the atom. This electron will go, it will hit this electron. So this electron now will be released. Now these two electrons will be released like this, and this one will go and hit another electron. This one will go and hit another electron of another atom. Are you getting the idea here? So this happens how? Because these electrons now, they are moving in a big space, so they become highly accelerated. So when they become highly accelerated and when they enter the n side, they go and hit, they go and strike the electrons which are of the atoms of the n side. So this electron, let's say this fellow is this one, let's say, okay? So this electron will go, and when it reaches, it goes and strike the electron of this atom which is present on the n side. Not this electron, it will go and hit those atoms, right? The electron of this atom. So now this electron will be dislodged, okay? It will be released from this atom, and itself it will go and hit other electrons of other atoms. This one also will go and hit other electron of other atoms. So like this, the process continues, and thereby a large current will start to flow. Okay, a large current, a large number of charge will start to be released, and a large current will start to flow. This current will increase abruptly like this. It will increase abruptly. Got it? And this voltage, when this happens, this is called the breakdown voltage. Is this clear here? So you can see here that the reverse characteristics is measured in microampere. Why? Because the current is due to the minority charge carriers, which is very, very tiny. Okay, so the current also is very, very tiny. But then as the width of the depletion layer increases, so these electrons, the minority charge carriers from the p side, when they cross over to the n side, they gain sufficient kinetic energy because they are moving in an empty space. They get the chance to increase the sufficient the kinetic energy. So what happens is, as they're moving very fast, they go and strike the electron of the atoms of this crystal. And those electrons, they themselves, they go and strike other electrons of other atoms. And in this way, a large number of charge is released. And due to the large number of charge, the current now will increase very largely. Okay, it will increase abruptly. So this voltage at which this happens, where there is a sudden rise in the current, that voltage is known as the breakdown voltage. This large current most of the time will damage the PN junction. So the PN junction is rarely used. It's rarely allowed to go beyond the breakdown voltage. Okay, so this is the reverse characteristics of the PN junction. All right.